Okay, Martin.
Okay.
Martin,
Yeah,
go.
Welcome everyone to this session 4 of Contributor Talks to CSL. My name is Martin Lange. I have the pleasure of chairing this session. I hope you can hear me okay, and also all the speakers. And without any further ado, I would say we'll move on to the first talk, which is given by Philippe Schnoebelen from Paris-Saclay, if I remember correctly. And it's on flat lossy channel machines. So please.
Okay, so you should see my slides now. On my affiliation, I've put in blue the recent change because our lab moved. We were joined by people from formerly LRI. The school moved, so if you don't have questions at the end, this could be a good topic for questions at the end of the talk. So the outline of my talk will be, two parts where I will do some recalls about lossy channel machines, verification, flat machines. Then 2 parts with the technical parts about analyzing the backward reachability algorithm in the case of flat lossy channel machines and using compressed words for better complexity. This is the part where I might skip some details if time is short. And the main result will be, the outcome of the talk would be NP completeness for several verification problems on flat lossy channel machines. So what are these channel machines? Just finite state machine with an auxiliary storage in the form of a FIFO buffer, also called a channel. So here you see a machine with 4 locations, and you move from one location to another with actions like writing. We use the exclamation mark, so writing A to the buffer or reading B from the buffer and so on. It's a classic model for communication protocols. In general, we have several concurrent machines, and then we talk of systems, channel systems. You can have several buffers, and there are several ways of enriching these classic models. Already, the basic model is Turing powerful. So verification techniques will have to make some assumptions or some restriction, like, for example, flatness. Here, I'm depicting the machine with its communication buffer, its communication channel, at the moment containing BAC, and I will explain the operational semantic just by examples. Actually, the machine is this current configuration, location Q1, content of a channel BAC, and by firing the only available transition, I will move to a new configuration, Q2, and now the channel as BACA can do another step, reading B from the channel, and you see that I read at one end, write at the other. This is the meaning of FIFO, and I can continue like this, and when I'm in Q3, I'm stuck because the machine would want to read a C from the channel, but there is no C available at the front of the channel. Well, we have a variant, lossy channel machines. It's the same model, except that messages that are in the buffer can be lost non-deterministically. So here, the same machine, I start from different configuration. The channel contains BAC, and the possible step would be to fire the first transition. The channel contains BACA. Now, if I read a B, well, maybe I can end up in this configuration. It's non-deterministic. You see that the final A has been lost. This can happen, and the machine has no notification. And now the machine would want to read a C. Well, it's possible. You just have to lose the A. And so there is also this possible transition now. The machine was not deadlocked. Okay, there's lossy channel machines. It was a model introduced in the 90s by Alain Finkel, Parosh Abdullah, and Ben Johnson. It turns out that this model seems, more complicated because of the added non-determinism. It turns out that it's decidable, and verification algorithms have been implemented for termination, for safety property. It's decidable, but it's hard. if I refer to yesterday's talk by Sylvain Schmitz, complexity would be hyper-Ackermannian, so even worse than the Ackermann function. And the model is used not only for verifying program communication protocols and so on, but also for deciding many variants of model logics and in other settings too. So it's an interesting formal model per se. I want to explain the algorithm that I will analyze. It's the backward reachability algorithm for lossy channel machines. We had an example yesterday by Sylvain Schmitz with counter machine. So I will do the same thing, maybe a bit faster with the channel machine. Let's say I'm in this configuration, Q2 and ABC in the channel, and I want to compute all the predecessor. So pre-star mean by an arbitrary number of transitions. So how can I end up in Q2 ABC? Well, I have to go backward. I have to, I see that there is a transition from Q1. So maybe if I come from Q1, I write a C, and then maybe I can end up in Q2 ABC. And yes, if I'm in configuration Q1 and AB in the channel, I could go in one step to Q2 ABC. In fact, anything above Q1 AB, meaning Q1 and anything in the channel that contain an A followed by a B is a possible predecessor, because by losing messages, I could be in configuration AB, and then writing C, I end up in Q2 ABC. So this is the meaning of this up arrow here. It means that all the configuration above this one, so it is Q1 and anything that has AB as a subsequence of the content of a channel. Now I can continue, and what more predecessor configuration do I have? So if I want to end up in Q1 AB or above, I can start from Q2, and I need to consume a B. So maybe if I were in this configuration or anything above, it would be a predecessor, and I can continue. So this would be a predecessor of this predecessor of this predecessor, and so on. And I can continue. And now I see that this configuration is already included in this set. This is a set because of the up arrow telling me to take everything above. And you see that BBAB contain BAB. So I don't have anything new to add. And in fact, I've finished computing the predecessor of this configuration. I have the full set if I take into account the upward closure. This phenomenon, stabilization, sorry for the spelling mistake, it's guaranteed by a WQO property of the subword ordering. This is an instance of what Sylvain Schmitz explained yesterday. And however, it can take a long time before we stabilize. In practice, it can be very quick on an actual example, but we can invent examples that will take very, very long time, that simulate a Turing machine with Ackermannian memory. Okay, so now the talk is about flat system. What is the flat system? It's flat if there are no nested cycles in the control graph. So here, well, this one is flat because the cycles, here I have one cycle, here I have another one, and here I have a second cycle. They do not intersect. But the other example is not flat because I have one cycle here and another one here, and they intersect here on this state. So what's the interest of looking at flat system? I'm sorry, here is another characterization of flat system is all their runs are in the language of this form. So I have, a finite number of possible choice. This would be in the DAG of directed, strongly connected components. And I will have a path in the DAG, theta 1, theta 2, until theta MP. And at each node, there is a potential cycle. So this is the star here, potential cycle. So I can take it any number of times. And the cycle is unique because of flatness. So why are these flat systems interesting? Well, it's because they are simpler. of course, it's a subcase, but actually they are simpler. In the case of counter machines, they have been studied by Kumonjorski already 20 years ago, and LTL model checking is only NP complete, while the model without flatness is Turing powerful. Some more recent results, for example, context freeness can be decided also quite efficiently. You can extend the model. So, for example, recently Ganti and Yossif showed that counter system with recursive procedure calls, so several stacks, and if you have flatness, then reachability is decidable only in non-deterministic exponential time. In the case of channel machines, already 20 years ago, it was discovered by Boisjani and Habermel that the reachability relation can be computed and represented as some kind of a decision diagram, so an automaton with constraint. Recently, Esparza, Ganti, Majumdar, also Finkel and Pravin showed that reachability and other verification problems are NP complete. And the topic of this talk is the case of flat lossy channel machine. Okay, so I should motivate the restriction. It's not just because it makes our problems easy. It's also because we use them actually. So we use them in bounded verification. You know, when you have a system to verify and you only verify runs of a certain shape. So here I will give a bounded language shape as the kind of behavior that I want to verify. And also, when we do reachability analysis with acceleration, this is exactly what we explore, you know, larger and larger bounded languages. And very often, this terminates in practice, even if the method is not complete in general. So now let me analyze the complexity of a reachability algorithm in the case of flat systems, and for this I just need to formalize what I illustrated on my example. So I will write X is a subword of W for channel content, and I will write from content X, I can move to content Y by these actions, and this is the definition. The larger than equal relation here or there account for losses. So now I can compute predecessor with this algorithm. It can be a functional program, a predecessor by a write action, by a read action, by a sequence of actions, and predecessor by a write action. This is this operation X/W defined recursively by these three clauses. It's in fact it tells me the largest. I'm sorry, it gives me the smallest d such that by the smallest y, I'm sorry, such that by writing d and losing, I can reach x or above. So this definition ensures that what I compute here, its upward closure is exactly what I want to compute. So the set of predecessor of the upward closure of x, sorry for the typo. And because this algorithm is deterministic, you see that if I fix the path, so sigma is a fixed sequence of action. If I fix the path, I have a unique minimal predecessor computed by this PR function. So now I will give a technical lemmas. So I consider an arbitrary sequence of action, but I write by alternating read and write. Since my AI and BI can be empty, this accounts for any sequence of action. And I will write U for the reading part, so the sequence A1, AR, it's a word of letters. And my first lemma will be that if my channel content is a power of U, then the predecessor by sigma, the minimal predecessor, will also be a power of U. By power, I mean that it can be a fractional power. So I just want that the exponent times the length of U is a natural number. Here's an example. If I take this sequence of action so that U would be AC, U to the 1/2 would be just A, and its predecessor by the algorithm of the previous slide would be AC. It is the power of U, now to the U to the 1. If I look at predecessor by sigma of ACA, I will get again ACA, so U to the 3 halves. On top of this shape, which is guaranteed by the third part of the lemma, I know that if my power is large enough, then in a sense, I don't have to do extra computation. I just have the remainder, the plus n, I just have to carry it around, or also minus n if my power m is large enough. This was the first technical lemma. Now I use it for predecessor by sigma several times. So let me take an arbitrary x. I compute the predecessor by k times the loop sigma, and I write yk for this minimal predecessor. So my result will be that each of these predecessors will have this shape, a power of u, and a prefix of x. This prefix will diminish, so the lk diminishes with k, the pk increase with k, and I can compute each of these, pk and lk, in polynomial time, polynomial in the size of k. Now, if I want to ask when do I reach stabilization, so let me write L of sigma x for the smallest integer so that my pre-star computation stabilize. That is to say that after so many computation of a predecessor, I have nothing else to add. So this is the main technical result. This stabilization length is bounded quadratically in my input. So length of x times 1 plus length of u, so the reading part of sigma. And the bound is tight. If I look at this example, the stabilization will always occur at times of x, size of x times 1 plus reading part of sigma. And now, with this theorem, I can bound the length of a minimal run in a flat lossy channel machine. So assume I have a reachability instance from qx to q prime y. Now I will look at the intermediary state, so I will look at the state, not just the channel content. So if I have a run like this, then there is a witness of this form. I start from some state. I do the loop on Q0 a given number of times. Then I move from Q0 to Q1. I do the loop a given number of times. I move from Q1 by theta 2 and so on. Eventually, I reach Q prime y. The part with the theta 1, theta 2, this is an acyclic path in my system. And each sigma I is the unique cycle, can be empty if there is no cycle, but the unique cycle that is visited a given number of times. And now I can bound everything here using the previous theorem. So I know that I can bound, because it's backward reachability, I can bound z prime n, it's y. I can bound any zi as the z prime I plus something that maybe has been added. I can bound the ni, the something that has been added by the loop. I can bound it with the previous theorem. What does it give in practice? It gives that nm and zm, the size of zm have quadratic size. Nm minus 1 and zm minus 1 have cubic size. And eventually, I have something that is in exponential size. And this bound is tight. We have paths that have exponential length. So I see that I'm running out of time. So I will skip the part where I explain how to encode this exponential length path with compressed work, so straight line program. And so I'm sorry, the details are in the paper. And the interesting part is that we have, in this algorithm, we have to decide whether a compressed word is subword of another compressed word. This problem is not polynomial time. while deciding if compressed word is a factor of another compressed word, the pattern matching problem. This would be polynomial time. But we have to do it in the case where y is not an arbitrary compressed word, it's a power word. So just some word to the k, where k is exponential, but written with a polynomial number of bits. And this can be done in quadratic time. And this is the essence of the algorithm for testing that a witness written with compressed word can be checked. Okay, so now with this, I can show that my problem is in NP, reachability is in NP. In fact, the problem is NP complete. It's NP complete already for acyclic machines or for single path machine where you have cycle but only one spine. We can adapt the technique to show that termination also is co-NP complete, boundedness, finiteness is co-NP complete, repeated control state reachability, bushy is NP complete. And to conclude with maybe extra minute over the time, well, this is the first case I am aware of where we use algorithm for compressed words as an algorithmic trick for reasoning not about compressed text, but at the data structure. In the field, we're more used of using regular languages, Pressburger formula as abstract data structure for infinite or large set. Here, it's SLP compressed word. It would be interesting to extend the upper bound technique for more general models. So the partially lossy channel system that were introduced by Chris Kroeger recently, the higher order channel systems. And of course, I've listed 4 verification problems. There are more general ones that would be interested to look at. Thank you for your attention.
Well, thank you, Philippe. So just imagine the applause here. Are there any questions? So if you do have a question, so this goes out to the audience, please raise your hand here via Zoom and we'll unmute your microphone. I can't see anything yet. So, oh, there is a question. Yes.
Sophia has a question.
Yes.
I'll ask her to unmute.
Yeah. Mm-hmm.
Can you unmute yourself?
Yes.
You can. Good.
Thank you very much. I was wondering, I was thinking about actor-based languages, and I was wondering whether there is a connection. I think that what you are describing is there is one cue and the cue changes over time. And with actor-based languages, there are many actors and each one has got a cue. So is there work where, what appears in one cue has been sent by another actor? So is there work where there is more than one cue?
Yes. Yes, and in particular, the result I gave accommodate several cues. Usually, when you have several components, several processes, and they can use queues in different ways. So, for example, there will be a dedicated queue for messages from process A to process B. You could have queues where everyone can write, but only one process can read. All these variants exist, and sometimes can be modeled by model, except that I will have to take a Cartesian product of processes, of machines to get a system, or it will be handled by some extensions.
Mm-hmm.
Yes, there is a rich body of literature on variants of this model.
Thank you.
Okay, thank you. I would suggest that we move on to the next talk, unless there is a very quick question. I can't see anything, so let's move on to the next talk, which means we're right in time. So the next talk is given by Karoliina Lehtinen from Liverpool University. I'm not going to read out all the co-authors because then the talk time will be used up. The title is The Best a Monitor Can Do. Monitor can do, sorry.
So yes, this is joint work with Luca, Aceto, Antonis, Achilleos, Adrian, Francalanza, and Anna Ingolfsdottir from various places, mostly in Iceland, Italy, and Malta. So as the title would perhaps suggest, the one-sentence summary of this paper is that given an arbitrary branching time property, we synthesize optimal monitors. Now, to understand what that means, here's the setup we consider, the following verification problem. We have a system that we treat as a black box, either because we don't have access to it, maybe it's intellectual property, maybe it is just too complicated, we don't have a good model of it, so we prefer not to look into it, or maybe we just don't want to do model checking yet, and if there are any low-hanging bugs that we can catch with a lower effort verification strategy, then we want to try that first before going into a more difficult commitment of model checking. So we have our black box system, which generates some execution that we have a monitor that can observe that execution. And the goal of the monitor is to say something about whether the system satisfies a specification. So after having observed some prefix of our finite execution, we hope that our monitor will be able to say, oh, I found a bug, this system does not satisfy the specification, or, oh, yes, now I know that my system is correct. Now, this is a kind of slightly different runtime verification problem from a monitor that would try to figure out whether this particular execution satisfies a linear time property. So here we are not interested in whether this particular execution satisfies a property. We are interested in whether the system that produced this execution satisfies a branching time property. So this is quite an ambitious ask, given that we have so little information about our system, namely just a growing execution that we are observing. So we have to accept that a lot of the time, our monitor is just not going to be able to give us any useful information, in which case we'll get an inconclusive verdict. So that's our setup. And the problem we would like to solve is, given some branching time specification, that specifies what our system should be doing, what's the best a monitor can do? So this monitor can just observe a single execution. What's the best this monitor can do? Now, this branching time setting seems very ambitious and is perhaps a bit unusual when usually we might be looking at linear time properties, but there is a use case for it. Namely, perhaps we don't want to treat our system as entirely a black box. Maybe we do know some prior knowledge about it. For example, we might know some that it satisfies some other branching time property that I'll call K. So this is our knowledge. And now we would like our monitor to be able to use the prior knowledge about our system to improve its monitoring. So for example, let's consider a system in which we have two components that can both write, they can open a file, close the file, and they can write into the file. Now, our example property is that I shouldn't close a file and then immediately try writing into it. That's our behavior that we don't want our system to be able to produce. Now, of course, a monitor for the system will observe an execution. If it does see that one of the component closes a file and then writes into it, it can flag a violation and say this system is incorrect because it produced this execution that witnesses the violation. Now, assume that I have some prior knowledge about my system that tells me that actually in my system, these two components, they're completely independent, and there's a scheduler that interleaves the executions from the two systems, and the scheduler can interleave them however it wants. And this tells me that whenever I see an event from component 1 followed by an event by component 2, my system could have also produced the execution where the events are the other way around. This gives me some information about the closures and the reordering of events that my system is able to produce. Now, using this knowledge, my monitor can do better than it could do without this knowledge. Namely, instead of just looking for the occurrence of close followed by write in one of the components, if it now observes close, let's say the first component, we have a first component close, it's followed by some events from the second components, which is then followed by a write in the first component. Because I know that my scheduling of the two components could be arbitrary, if I witness such a trace, then I know that my system could have also produced the original trace that witnesses the violation. So using this additional branching time knowledge about my system will allow my monitor to be more powerful. So now the question is, given a property and this knowledge, how do you combine them to give you this monitor and an optimal monitor, which does the best it could possibly do? And it turns out that to do this, we just need to compute the optimal monitor for the conjunction of the property and the knowledge. And that will be the best we can do. So this problem of integrating assumptions or prior knowledge into the monitor reduces to the problem of generating an optimal monitor for a branching time property. And here it should be clear that we should be interested in branching time properties, since this type of knowledge of the independence of two components, for example, that is inherently branching time. So we can't just go back to the linear setting if we want to integrate this type of knowledge into our monitors. Okay, so that is the main contribution of this paper, is given this branching time property, let's compute the optimal monitor. Now let's go into a little more detail. Maybe what exactly do I mean by an optimal monitor? So given a property, its optimal monitor, and I'll focus on rejection monitors that identify violations, but obviously we can do the dual. So here the optimal monitor, it is a set of traces, the set of traces such that finite traces, such that if a system can produce this finite state, then I know that it violates the property. So it's the set of finite trace witnesses of a violation of my property. So this is a set that I would like to have, that my monitor would be able to identify to flag violations. So how do we compute such a set? Well, you want to start from a property expressed as a formula of your favorite logic. We use the modal me calculus or Hennessy-Milner logic with recursion, which allows us to do this for regular branching time properties. Now, there are some properties for which this is easier to do than for others. And for one set of properties, this is particularly easy. And this is the set of so-called monitorable properties. What do we mean by monitorable property? Well, it's the set of properties where every violation of this property, so any system that violates this property, produces one of these finite trace witnesses that witnesses this violation. So it is so a property is violation monitorable if for every system that violates it, there exists some finite trace produced by that system which witnesses this violation, such that any other system that would produce this trace also must violate the system. So these are the traces which when my monitor has seen them, it can terminate and say there is a violation. So for some properties, this is the case. And so my colleague's prior work tells us that the set of these monitorable branching time properties can be captured by a fragment of the modal me calculus, which is the following. It has true, it has false, it allows for conjunctions, it allows for universal modalities. So these are formulas that say for all A successors, some formula holds, and they allow for a greatest fixed point operator, which allows us to express that something always holds. And so this fragment of our logic, it captures exactly the monitorable properties. So anything that has this set of traces will be expressible in this logic. And if we have a formula in this logic, then we know it is monitorable. And what my colleagues also show is that if we have a formula in this fragment, then it is actually very easy to compute this set of finite traces. So it is easy to compute the monitor syntactically from the formula in this fragment. Okay, so these are the properties for which this problem of generating an optimal monitor is easy. Now, the difficult bit and the bit that we, so the new bit, let's say, the new bit in this paper is what do we do if we have a formula that is not in this monitorable, that is not in this monitorable fragment. So we start with an arbitrary property of the Middleman calculus, and now we make the following observation. If my input formula happens to imply some formula that is in this monitorable fragment, if my property implies some other property, then if I have a monitor, an optimal monitor for this consequence property, then I can also use it to identify some violations of my original property. So a monitor for a consequence is a monitor that is sound for the original property in the sense that it does not give any false verdicts. However, it might also miss some verdicts that it could give. Now, every property will imply some monitorable property, namely trivially true, but it might also imply some stronger monitorable properties. And in fact, what we want is we want the strongest monitorable consequence of a property. So given an arbitrary property, we would like to find a formula in our monitorable fragment for which we can easily compute its optimal monitor and then use that to monitor our original formula. And it turns out that is the best you can hope for. That does give you an optimal monitor for the original formula in a technical sense too. So that's what we'll do. Here's an example of what the strongest monitorable consequence might look like. If we have a property such that, for example, on all executions, eventually I see the event write, but I do not see it before another event read. And on some execution, write occurs infinitely often. So this is a branching time property. Let's say we are interested in this property. It is not monitorable. For example, this write occurs infinitely often. That is not something that can be witnessed by a finite trace. Eventually, write occurs is also not something that has violations that can be identified from a finite trace. So overall, this property is not monitorable. However, it does have a monitorable consequence, and its strongest monitorable consequence even is that write does not occur before read. So this is something that we can monitor for, and the idea is, given this arbitrary property that may have a lot of non-monitorable aspects to it, we want to extract this simpler monitorable formula and then use that to generate our monitor. So that's the technical contribution of the paper. Is we start with our modal mu formula and we compute syntactically its strongest consequence in this fragment from where generating the monitor is prior work. So how do we do this? I'll give a sort of fairly quick overview of what this syntactic transformation looks like. So this is our goal fragment. So it doesn't have any least fixed points. It doesn't have any existential modalities. So you can't use this fragment to say there is an A successor where something happens, and it doesn't have any disjunctions. So we have to somehow get rid of all of those. The first step is to turn our formula into so-called disjunctive normal form, which is due to Janin and Valukiewicz. And this corresponds kind of morally to turning an alternating automaton into a non-deterministic automaton. So essentially we are restricting the conjunctions, which will just make the manipulation of our formula somewhat easier. Then once we have a formula in this disjunctive normal form, what we are going to do is that we're going to remove all the existential modalities. We need to remove them because our fragment, our goal fragment, does not allow for them. And here, the idea is that, well, if your formula contains there existing an A successor where something happens, that is just not monitorable at all. There is no trace you could observe that would tell you that there is no different A successor where something may hold. So essentially, we can just remove all the existential modalities. Now, of course, this does not preserve semantics, but that's okay. We don't have to preserve semantics. We just need a formula that is a consequence and that has all the same monitorable consequences. So we'll remove this. And here it's very important that we are in this disjunctive normal form. Otherwise, we might have some conjunctions that interact. So for example, if a formula says there is an A successor where a formula F holds, but for all A successors, some formula F prime holds, perhaps F and F prime are building complements of one another. In this case, this formula is equivalent to false, and we can monitor for its violations because everything is a violation. So it's very important to be in disjunctive normal form, and then we can remove our existential modalities. Once we have removed our existential modalities, we can replace our least fixed points by greatest fixed points. Here, for this to be, again, we don't preserve semantics, we just want to preserve consequences. And here, monitorable consequences, that is. And here, this transformation also only works because we have just removed the existential modalities. Because if we have least fixed points and existential modalities, then we could write a formula that is unsatisfiable and therefore monitorable. So it's important to do things in the right order. Once we have removed the least fixed points, all we need to do is remove the disjunctions, and we'll end up in a formula in our fragment. Now, remove the disjunctions is not as easy as these previous two transformations, and that will take a bit more effort, and it is a kind of subset construction type thing. And that is kind of, does resemble morally determinization. And then what you end up, if you take all these steps, you will end up with the strongest monitorable consequence of your original formula, and it will be in this fragment from where we know how to produce monitors syntactically. Now, since we have a step that removes, well, nearly removes alternations, and we have one step that removes non-determinism, this whole thing has the flavor of determinization. So one of the downsides of that is that it is a worst case double exponential. That is to be expected because the corresponding problem on linear time is also double exponential and also has the flavor of determinization. So that's not particularly surprising. I wouldn't be particularly worried about it either, because as you see, most of these steps tend to prune large parts of the formula out. So you do end up simplifying the formula a lot, although you do also risk this blow up. Okay, so that's the kind of technical bit of our transformation. Now, the fact that we work with the modal new calculus, it allows us to, well, it's very expressive logic, which in particular means that the strongest monitorable consequence is always defined and is always expressible in the same logic. That's not necessarily the case for all logics. I do think it is the case for LTL, for the linear time setting. However, there the complexity becomes really scary, at least to the best of my knowledge, because the only way I am aware of getting the strongest monitorable consequence in LTL is to get a deterministic automaton and then turn that back into LTL. And I'm not aware of any way of doing that, which does not involve a non-recursive blow up. So there the complexity can be really scary. Perhaps there's a better way of doing it, in which case do let me know. So yeah, that depends a bit on the logic, how well behaved it is, whether we can do this syntactically. But in this case, we can. So we only deal with regular properties expressible in our logic. we could do, of course, the same thing for non-regular properties, and there we might have some other interesting questions, namely, here our monitors are also regular sets, but perhaps once they're no longer regular sets, maybe you're interested in bounding the resources, in which case you can ask the strongest consequence that is monitorable with respect to whatever restricted set of monitors you want to be using. I think I will conclude there, as that's the end of my time. To sum up, we compute optimal monitors for arbitrary regular branching time properties, which allows us in particular to solve this problem of how to integrate branching time knowledge into your runtime verification monitor. Thank you very much. I'll be here for questions and at the gather afterwards.
Okay, thank you for the interesting talk. So before we go to question, I think I have to apologize. I got the affiliation wrong, right? So if I saw the title slide correctly, I said Liverpool, and I think I read something else there.
Yes, that's a very recent change. Okay. I haven't managed to change my website. Yes, I'm in ex-Marseille since 2 weeks.
Okay, yeah, I could know that. I've been locked in this house for a year, so. Are there any questions? Again, please raise your hand here in Zoom. Otherwise, I'll ask. So if I understood this so correctly, then this definition of a monitorable property where it actually contains two things. Yeah, so you want it to be violatable by one finite trace, right? So there's two things in there. So it has to be a single trace and it has to be finite. Yeah. And so I guess my understanding is you don't have disjunctions in the logic here because then you would need to violate by a set of traces rather than a single one, for instance.
Yes.
Yeah? And what about relaxing this other side? So the finite, the requirement on being finite. I mean, one could look at infinite traces as violations to properties.
So that's
Any point in doing this?
So that's a good question. So I guess so coming from the kind of runtime verification, that's the kind of like the kind of guiding principles is you have a verdict after observing a finite execution. But from a language theory perspective, I agree that one could also a set of branching time properties where failures are witnessed by a trace, finite or infinite.
I guess then you would sort of need to include, or it could include, least fixed points in this logic, and I don't think that from runtime verification it really is. It's a big issue because I mean all the results about regular properties are that basically eventually we'll go into some loop. You could say, well, at some point I'll see this is just looping around, and I can say, okay, this is good enough for me, sort of in practice. So I don't know.
Yeah, so I agree that I would imagine that the change in the fragment is exactly allowing for least fixed point. From then the kind of practical perspective, perhaps it can be justified by some kind of adding, as you say, adding some additional powers to the monitor of deducing or looking at states and deducing that you are now in the infinite behavior, which kind of goes beyond the very classical restrictions. But yeah, that's a very reasonable, in my opinion, it's a reasonable setup that would give very reasonable language questions.
Okay, so if there's no other question, I'll ask a very quick one. So you mentioned non-regular properties at the end. How would you specify them?
So there, I guess it would. So in the linear setting, you can of course talk about push-down automata and that kind of things, which I guess you can also start defining on branching time systems, which I imagine someone has already. I imagine that it's not a completely new idea, but I'm not familiar with the kind of automata or logics that you use to, say, describe context-free languages on trees. But
okay.
yes,
Because so I mean I can immediately think of a few, but we will definitely take this somewhere else, this discussion. And
there I can so what I think is an interesting thing that happens is that you have a difference. So you probably want your monitor to be a deterministic machine, but then if you're on context-free languages, you might have. Not everything is determinizable suddenly, so you also have to take that into account.
That's going to be a problem. Anyway, okay, so thank you very much again, and we'll move on to the third talk in this session, which is going to be given by Valentina Castiglioni from Reykjavik. So, but I think I got this one wrong. Yeah, did I? Yes. Thank you. And if I'm informed correctly, then this is a pre-recorded talk, right? So
Yes.
don't try to ask questions in between. We'll do them at the end.
Okay, I'll just share the video in a moment.
Hello everyone, I'm Valentina, and I'm going to tell you a bit about the work that I've done with Luca, Van, Anna, and Bas. Our objective was to find an answer to the question that you see on the slide. Are two binary operators necessary to finitely axiomatize spiral composition? Well, the good news is that we found an answer. And the answer is yes, we need two auxiliary operators to get the desired finite equation of axiomatization. This could be it, but for a complete and correct technical development of our results, it was necessary to work under some assumptions on the operators. But these assumptions are perfectly natural and reasonable, at least to us. But it is undeniable that in this way, we could only obtain a partial answer to the question. But to tell you why this is still meaningful, let's formally introduce the problem. So given any operator F, we call CCSF the relabeling and restriction-free fragment of CCF. The challenge isn't to discover whether there is a binary operator F such that the binary operator. And in this paper, we partially solved the challenge by showing that for an operator F that can be defined under the previously mentioned assumptions, bisimilarity has no finite equational axiomatization over CCSF. But despite being only a partial answer, I can give you 3 reasons why it is a valuable answer indeed. Well, first of all, ours is the first non-finite axiomatizability result that applies to an entire family of languages. Usually, in equational theory, you fix the language and you study the equational axiomatization for a chosen congruence over it. But in this case, we do not have a single language because the operational semantics of the operator F is not given, is not known a priori. And this is the main reason why we needed to introduce some simplifying assumptions. We could not reason on any possible binary operator. The case complexity in the technical proofs would be simply impossible to manage. So we use the assumptions to restrict the set of operators to a meaningful one. And still, our result holds for all the languages having one of these meaningful operators. The second reason is that our result allows us to establish the canonical status of left merge and communication merge, namely the 2 binary operators that were used by Dijkstra and Klopp to obtain a finite axiomatization of spiral composition modulo bisimilarity. This means I mean, having a canonical status basically means that they were not just a lucky guess, and there are not plenty of alternatives to them. It's their relation to paracomposition and the other CCS operators that actually gives the finite axiomatizability result. And finally, our study also gives an insight into which properties auxiliary operators should have in order to allow us to obtain finite axiomatization of paracomposition. And this is, of course, strictly related to the first two contributions. So now that our specific contribution has been settled, let's see how we got there, starting from a bit of context. Usually for analysis or verification purposes, it is important to be able to establish whether two processes, or more generally, two descriptions that are syntactically different, describe the same thing. And on one hand, this can be done by means of behavioral equivalencies that allow us to establish whether two processes can be distinguished for their observable behavior. And therefore, they are equivalence relations defined on the semantics of processes. On the other hand, the study of the equational theory of a language allows us to establish a syntactic equivalence of processes. It is in fact based on a set of syntactic equations, also called axioms or reduction rules. And these equations are defined over terms that allow us to replace equals by equals. So one of the key problems in concurrency is to find an equational axiomatization of an equivalence. And because at that point, if we have an equational axiomatization, then we can use the axiomatization to characterize the semantics of a process algebra in a purely syntactic fashion, and independently on the technical details in the definition of the semantics itself. And at the same time, the equational axiomatization can give us some insight into the differences between the various semantics, thus helping us to choose the most suitable one for our purposes. And finally, an equational axiomatization may also form the basis for program verification tools based, for instance, on theorem provers. So let's briefly see on what equational axiomatizations consist. An axiom system is a collection of syntactic equations over the considered language. We then consider a congruence over the same language, namely a behavioral equivalence that is preserved by the language operators. But basically, the equivalence R is a congruence if the behavior of a composition of processes is not affected by the substitution of a component with an equivalent one. We say that an axiom system E is sound and ground complete modulo the congruence R if two processes can be proved equal from E if and only if they are related by R. And here soundness is the left-right implication, whereas ground completeness is the opposite one. And among all possible axiomatizations of a congruence, we are interested in those that are finitely based, namely those for which there is a finite axiom system from which we can derive all the valid equations over the language. So we consider the language CCS, in which we have the null process, variables, prefixing, non-deterministic choice, and of course, paracomposition. And on the slide, we have the operational rules defining paracomposition, where the first two rules on the slide describe the purely interleaving behavior of the paracomponents, while the last two rules are for the communication. And in CCS, two processes composed in parallel can synchronize or communicate if one can perform a transition labeled with an action name, and the other one can perform a transition labeled with the action coname. A process is a closed expression, of course, of the language. Our congruence of interest is then bisimilarity. We say that two processes are dissimilar or bisimulation equivalent if and only if they can mimic each other's actions, reaching processes that are related by the same bisimulation equivalent. Now, one can provide a sound and ground-complete axiomatization of bisimilarity over CCS, but a first fundamental result is a negative one. Farah and Moller proved that bisimilarity does not afford a finite equational axiomatization over CCS. And the idea behind Moller's proof is that if we consider the parallel composition of a process that can only perform action A with a process, say P, having a large branching degree, then no finite sound axiom system E over CCS is powerful enough to entirely expand the initial interleaving behavior of the term. Consider, for instance, this term here, where n is chosen larger than the size of E. This means, for instance, that E contains all instances of this equation where the sum is taken from 1 to k, for a k that is smaller than n. Then there is no way to combine all those instances and maybe other axioms in an equational proof to derive this particular equation for the chosen n. But don't worry, there is still hope. And in fact, Bergstra and Klopp provided a finite ground-complete axiomatization of bisimilarity over CCS by adding two auxiliary operators to its syntax, the left merge and the communication merge. Intuitively, left merge expresses the purely interleaving behavior of parallel composition, while communication merge, of course, expresses the synchronization. So in this way, parallel composition of two terms can be naturally expressed as the non-deterministic choice between their left merge composition and their communication merge composition. And allow me to stress that both the auxiliary operators distribute over non-deterministic choice, which basically means that we can now deal with processes having a large branching degree without having to completely expand their behavior. Well, so far, we have established that if we want to finitely axiomatize parallel composition, then we must add some auxiliary operator to CCS. So a natural question is then whether there is an alternative to the pair left merge communication merge. In particular, we are interested in verifying whether there is a single binary operator that we can use to obtain the finite axiomatization. And as previously discussed, we expect a negative answer. And my personal intuition on this is that if you introduce a single binary operator to express equational parallel composition, that operator needs to be able to express both interleaving and synchronization. So since we cannot at that point separate them, it is very unlikely that we will be able to distribute their behavior over choice. And so the only thing that we can do is still to expand the initial behavior of processes with large branching degree. So we end up again in the case studied by Farah. But besides personal interpretations, this negative answer is still a conjecture. Because as we said, the only way we had to formally prove our results was to introduce some simplifying assumptions. So let's see which are these assumptions. First of all, we assume that the operational semantics of the operator F is specified using CCS-like operational rules, which, for those of you that are familiar with it, means that the rules for the operator F are in the decimal form. The second assumption is that power composition can be expressed equationally using F. And we proved that suitable expression is the one given here on the slide. And this expression also resembles the equational expression of parallel composition given in terms of the left merge and the communication merge. And there is also a third minor assumption that is purely technical, and it only played a role in the proof of a lemma. For those of you who are interested, it states that in the targets of the conclusions of the rules for F, we cannot have a nesting of operators, especially a nesting of F operators. So, thanks to these assumptions, we were able to identify all meaningful operators. This means that we have derived all possible forms of the operational rules for an operator that satisfies them, obtaining 3n+1 possible operators for a set of actions composed by 2n+1 elements. For instance, if we consider the case of 3 actions, namely action A, its codename, and action tau, which is used for the communication. Then we obtain that to guarantee the soundness of this equation here, then for each action, operator F needs to have at least one rule guaranteeing that at least one of its arguments is allowed to perform that action, and at least one rule allowing for communication. We have also proved that target of all such rules has to be bisimilar to power composition of terms. We are not saying that these targets are all the same term, but whichever is the target, it has to be bisimilar to the power composition. This was our first result, and we then showed that no meaningful operator distributes over choice in both arguments. And then we split the proof of the negative result into two main parts. Namely, firstly, we proved the negative result for all meaningful F that distribute over choice in one argument. Then for those that distributes in neither argument. And again, the reason for this distinction is purely technical. So just to give a very high level idea on how we have proved our results, I'll just give you a little example. We have applied what is called a proof theoretic approach to negative results. This consists in finding for each finite sound axiomatization E a property of equations that is satisfied by all instantiations of the axiom Finitely. It is preserved by the rules of equational logic, but it fails for some sound equation. The idea is that this equation that needs to be added to E to obtain the ground completeness, and we can repeat this procedure for infinitely many equations. So as an example, again, for three actions, A, codename, and tau, one of the meaningful operators is given by the rules that you see here on the slide. Basically, only the transitions of the first argument of F are mimicked, and they lead to a term that is bisimilar to power composition. And we allow any form of communication. So both arguments of F are allowed to communicate with transitions having the name or the coname of action tape. And we have proved that whenever E is a finite sound axiom system, that E cannot prove equation En for n that is larger than the size of E, where this strange symbol here simply denotes the sum for J that goes from 1 to E of trace of length J of alpha actions. And here the property of equations is to have a summand that is bisimilar to this F term here. So to conclude, the obvious next step would be to find a way to get rid of the simplifying assumptions. For instance, we would like to investigate the operators with operational rules in the GSOS format in place of the decimal format. And we are looking for results in a universal algebra that could help us to directly extend our work to a more general setting. But on this matter, we are definitely open to suggestions and to corroborations. So if you have an idea or the 12% of a plan on how we could do this, feel free to contact us. Here is my email, but you can contact any of us. Now, if you have any question, I'll be glad to answer them.
Okay, thank you very much. Sorry, I'm just getting a bit confused by what I see here now. Are there any questions? So in which case, I will ask a quick one to give you some more time to formulate others. What exactly is meant by the general case at the very end was on the last slide? Was it that it's not binary, but of arbitrary?
No, it is still a binary operator. It was just a small example of how we have technically developed our negative results.
No, but you just said said something about extending this to the general case.
No. It was to get rid. Our idea is now to extend our results in the sense that we used free simplifying assumptions.
Okay. Mm-hmm.
And some may say that, okay, but still you don't have a real answer to the original problem because you are working under these free assumptions. So we are now we are wondering whether there is a way to get rid of these assumptions. So
okay, yeah. Mm-hmm.
This is how we mean to extend the results.
Yeah. Mm-hmm. Actually, so personally, I don't think that these assumptions are too bad, but what I was wondering is, so there was this axiomatization, which included these, if I remember correctly, they're called left and communication merge operators. What's wrong with them? Why go and say, look, we need to get rid of them? There's too many. We only need one. So
our point is that actually to somehow prove that there is nothing wrong with them, and that both of them are actually necessary. So, but to prove something like this, we need to prove that you cannot actually do better in the sense that you cannot get rid of one of those. But they are perfectly fine. We love left merge and communication merge. So it was just maybe out of curiosity at the beginning, whether we can actually achieve a finite ground complete axiomatization of power composition having just one auxiliary operator. But,
okay, yeah. And so where's this all going? So I mean, this is about one operator, the parallel composition in one process algebra, CCS, with respect to one process equivalence, namely bisimilarity. So there's this three-dimensional space of extending this, right? So you can be working on this for the next 8,000 years, doing all process algebras and everything. Is this the goal now, to just sort of continue examining everything there?
maybe luckily there are not many equivalencies for which there is no finite ground complete axiomatization for parallel composition. So if you imagine of Rob van Glabbeck's spectrum, everything below ready simulation already has a finite complete axiomatization for parallel composition. So just the equivalencies not having these finite axiomatizations are, of course, pi simulations, then the nested simulations, possible and impossible futures. So it just is 4 classes of equivalencies. But let's say that from that point of view, our idea is just to focus on pi simulation. Then if I don't know whether it could be interesting to investigate the same problem for other languages than CCS. But let's say that first of all, we want to obtain all the results regarding CCS and pi simulation, pi similarity.
Okay, yeah, get it. Thank you. Okay, so used up the time here as well quite nicely, and I would suggest that we move on to the last and 4th talk of this session, which is given by Guillaume Geoffroy. And for fairness reasons, I will also not read out the list of co-authors here, even though it would be a lot shorter than in the other cases. I will read out the title, though. It's on the partial metric semantics of higher order types and approximate program transformations. Here you go.
Okay, so good morning, everyone. This talk will revolve around the following question: how to measure distances between higher order programs. And in order to answer this question, we must first ask, why do we want to measure distances between programs? And there may be several answers, but the one I'm interested in is I want to measure distances between programs in order to justify approximate program transformations. Consider, for example, this infamous piece of code from the video game Quake 3 Arena. What it does is compute the multiplicative inverse of the square roots of a floating point number. And it does this much faster than the corresponding standard library function, but at the cost of a small error in the result. And if we were to use this code in any piece of formally specified software, well, we would need a way to mathematically state within the formal specification that this small error is acceptable. So we would need an approximate specification. Now, this substitution, replacing the square root function from the standard library with this piece of code, is sort of everyone's dream program transformation. See, this is the actual square root function, and this overlaid on it is the approximate version. So you see, you get a very small relative error, in fact, less than 0.2%, and that holds across all orders of magnitude. So this is sort of an all-purpose program transformation. It can be used in pretty much any context. On the other hand, suppose you wish to replace, say, the sign function with its linearized version, the identity, then the relative error can grow arbitrarily large. So whether this substitution is actually valid depends on how large an error can be tolerated in the context in which you use the function. And it goes the other way too. Let's say the validity of the substitution depends on whether the context uses this function on arguments that are small enough. So to sum up, we want to measure distances between programs in order to justify the substitution of a program or part of a program with a close enough approximation of it. Whether this substitution is close enough depends crucially on the context, and interaction goes both ways. So these ideas are explained in an article by Dal Lago, Gazzo, and Yoshimizu called Differential Logical Relations. and they sum up these ideas in one picture, which I show here in a slightly modified version. So you see here the program substitution, the approximate program substitution, the all-important context, and the two-way interaction, inputs and outputs. Now, the article on differential logical relations also proposes a realization of these ideas in the form of a concrete notion of distances between programs. Here's how it works. If you have two programs of type real, that is to say, two programs that evaluate two real numbers, real values, then the distance between them is defined as usual. On the other hand, if you have two programs that compute functions from real numbers to real numbers, then the distance between them depends on where they are evaluated. So the distance between them is a function rather than just a real number. But in fact, you want to be able to compute distances in a compositional way. That is to say, if you know the distance between the sign function and the identity, you want to be able to compute the distance between their outputs, not just when they're applied to the same inputs, but also when they're applied to slightly different inputs. So instead, in fact, you need to define the distance between the function in this way. See, for all reference points x and all error threshold e, you say the function between the two functions is a function that for all reference points x and all error threshold e gives you the maximum error difference you can obtain in the output if you substitute one function for the other and change the input by at most e. And this is how you define distances. This is how they define distances between functions on all simple types. And now an important remark is that the distance between a function and itself with this definition is not necessarily the constantly zero function unless the function is itself constant. For example, here's the distance between the identity and itself. You see, this is not the zero function because the error threshold may be non-zero. That's one thing. And besides, you see, the distance between two programs of the same type A is not necessarily a real number. We saw here that it can be a function, for example. So it's not necessarily a real number, but an element of some structure that depends on the type A. This structure should support comparison, suprema, and in order to write triangular inequalities, it should support addition. And it turns out there's actually an off-the-shelf mathematical structure called quantals that does exactly this. And how quantals work exactly is not really relevant here, but the important point is that they support these three operations: addition, comparison, and suprema. So to recap, in the article on differential logical relations, each type A is interpreted by a set of denotation, a quantal of distances, and a distance function. A distance function such that the distance between an element and itself is not necessarily zero. So take this distance function. Even if we ignore the fact that it's not real valued, and the whole point of choosing quantals is that we can do that, well, because of these non-zero self-distances, we don't have a metric space. Fortunately, there exists a well-behaved mathematical structure that can accommodate these non-zero self-distances. They're called partial metric spaces, and they're obtained by taking the usual definition of metric spaces, removing the requirement that the distance between an element and itself be zero, and replacing the usual triangular inequality by the following modified version, in which you've added on the left-hand side the self-distance of the intermediate point, which is now not necessarily zero. The trouble is the distance given by differential logical relations does not define define partial metric spaces. It doesn't satisfy this triangular inequality. For example, consider these three functions f, g, and h. So you will measure the distance at a specific reference point x with a specific error threshold epsilon. And if you look at the distances, you see that the sum of the distance fg plus the distance gh is exactly the distance fh. And so there's no room left to add the self-distance of g. So you don't have the partial metric inequality. So that's the context. Now, the objective of this talk and the paper that goes with it is to introduce two new ideas that come from a common change of point of view. The first idea is that is a slight change in how distances are measured, which turns out to produce actual partial metric spaces, so with the full inequality. And the second is that independently of distances, approximate semantics can be studied using Cartesian lax closed set enriched categories. And the changing point of view that's behind both of them is to forget about the reference points. For example, instead of thinking, okay, this program returns 1 plus or minus an error of 0.1, we'll simply think, okay, the value returned by this program is somewhere in the interval 0.9, 1.1. Here's how it works in the example from before. So you have your three functions. You'll measure the distance, the distance this time not at a reference point x with a given error threshold, but instead on the interval x1, x2. Okay. In absence of a reference point, the only way you can define the distance between two functions on this interval is as the length of the smallest interval that contains the output of the functions. So for example, the self-distance of g is the length of the self-distance of g on this interval is the length of the smallest interval that contains the image of g on this interval. It contains the image of both g and g, so just g. The distance between f and g is this. You need to contain the image of f and the image of g. Distance of gh is this. Now, if you add the distance fg and the distance gh, you see that you get more than the distance fh this time, because there is some overlap. And in this case, this overlap is exactly the self-distance of g, but more generally, since this interval must by definition contain the output of g, and this interval by definition must also contain it, then the overlap must at least be the self-distance of g. So in the end, you do get the partial metric triangular inequality just by doing this modification. And so that's at first order. More generally, if we want to define a distance on all simple types in such a way that we get every time partial metric spaces, here's what we do. We define, for each type A, we define inductively a set of denotations of type A with the definitions you would expect. We define a set of intervals of type A. That is to say, for each non-empty set of denotations of type A, you say either this set is an interval or this set is not an interval. So for the base case real numbers, you take the non-empty compact intervals in the usual sense plus R, and you say these are the intervals. For products, you say an intervals on the product is a product of intervals. And for functions, it gets a bit more complicated. See, you take for each function from denotations on A to intervals in B, you can interpret this function as a specification on functions from A to B. You say for each point in A, the result of your function must be in some interval. And so for each such specification, you get a set of function that satisfy the specification. You say this set is an interval, and the intervals of the type A to B are exactly the sets that can be obtained from one such specification. So you got your intervals. Now, for each type A, for each type, you also define a quantile in which you will measure distances. So the definitions for real numbers for the base case and products are quite clear. For functions, for function types, you say a distance between a distance on the function type A arrow B is a monotone function from intervals in A to distances on B. And the reason you do this is that for all intervals of type A, you define a diameter function on, so a function that gives a diameter to all intervals. And so with straightforward definitions for real numbers for the base case and product types. And for function, you say, okay, the diameter function on the type A arrow B takes any intervals on functions, any interval on inputs, and returns the diameter of the set of all the outputs you can obtain by taking a function in this interval and an input in this interval. And so you've got these four things, sorry. And so the notations, intervals, distances, diameter function. And with that, the distance between two programs is defined, as in the example with the functions, as the diameter of the smallest interval that contains your 2 points. And the question becomes, with this definition, do we have the triangular inequality of partial metric spaces? And it turns out that this property cannot be easily proved by direct induction. Instead, you need to prove a property on the diameter function itself. And if you look at what happens on the type of reals, you see that you take any two intersecting intervals in R. The sum of their diameter is the same thing as the sum of the diameter of their intersection plus the diameter of their union. This property is called modularity, and it turns out that it is partly transmitted inductively to higher order types. What I mean is that for all types, an easy induction shows that for all intersecting intervals in these types, you have this inequality between the diameters of your two intervals, the diameter of their intersection, and the diameter of the smallest interval that contains both of them. And so this can be proved this time by induction. And you can prove that this property entails the triangular inequality of partial metric spaces. In fact, I'm using exercise and I encourage you to try it on your own. So anyway, that takes care of the first idea. We saw that by changing slightly how we measure distances in a way that reflects the absence of a point of reference, we could obtain actual partial metric spaces, modulo the fact that they're not real values. Now, forget about distances and let us go back to the idea of approximate specifications. If you have two types, A and B, we would like to define what it means to approximately specify a function from A to B. And given what we've just said, we would like to, the first idea would be to say, okay, an approximate specification for functions from type A to type B is just an interval in the type of functions A to B. The trouble with this is if you do that, there is no way of composing approximate functions in a way that is associative. So they do not form a so types and approximate functions with this definition would not form a category, which is not very convenient. Instead, what you can do is say, okay, an approximate function from A to B is a monotone map from intervals of A to intervals of B. This times these are regular set theoretic functions, so they compose in a way that is associative, and they do form a category. And now it's not too hard to see that there is a sort of two-way correspondence between approximate functions and intervals of functions. And this looks like the sort of correspondence you would have in a Cartesian closed category. And if these two things were inverse bijections, you would actually have a Cartesian closed category. Instead, but they're not, so you don't have a Cartesian closed category. Instead, you have these two inequalities, and this turns out to entail a well-known property called Cartesian lax closedness. And if you try these constructions with intervals and approximate functions on any functional language, you will always get a Cartesian lax closed category. So this suggests that Cartesian lax closed poset enriched categories may play a similar role in approximate semantics as Cartesian closed categories play in traditional semantics. Well, that's all. Thank you for your attention. And if you have any questions, feel free.
Well, thank you for the talk. And as before, so the call is out for questions. Please raise your hand on Zoom if you have a question here. Otherwise, I'll just ask one. So from what I understood is, so you compute these distances, etc., from certain, so let's say, base values or types using products and function spaces.
Mm-hmm.
So what does that now mean on the programming language side? I mean, what programming languages do you cover? I mean, this looks like only simple lambda calculus.
So right now, what's the only thing that's covered with this is just, let's say, lambda calculus, for example, lambda calculus with simple types and maybe a recursion operator. So, for example, I don't have for now a good way to measure distances between some types. So there is a good notion of intervals on some types. So the second part sort of works for some types, but not the first part, not yet.
So the example you gave at the beginning about the square root, this was, I mean, this was something like C or C++, I guess.
Yeah, this is
so
C.
How far away are you from doing that?
So the wholes of C or C++, I think quite far, because now this is a language with the side effects, so it's a bit more,
okay,
more complicated.
So there is another question here, Jean.
Yes, thanks for the nice talk. Great new ideas, I would say. I was wondering whether you might be able to apply that to probabilistic programs, which in my opinion is the real challenge.
That's what I'm just starting to do right now.
Okay.
Because I mean, first I needed let's say a good exact semantic for probabilistic programs, and so I was working on that, but now I think I have something that works, so now I'll be trying to combine both things, and yeah, that's pretty much, yeah.
Okay. Thank you.
Okay, thanks. So I see no further questions, and we're also done with the time. So I would like to thank all 4 speakers of this session again, and also the organizers here for running this quite smoothly. There's 2 more things I'd like to say. So apologies for the loss of sound during the 3rd talk. Someone has made themselves known to me as being responsible for this, and I shall take appropriate action of punishment. I actually didn't notice. I actually didn't notice anything, but maybe I fell asleep or whatever. Sorry. And the other thing is, yes, I would like to ask the speakers to go to the gather space to be available there in case there are more questions. And of course, I'll invite all the attendees of this session to go there as well and yeah, merge in this virtual environment. Okay, so thanks. And